Trying to choose a speaker for a new build? Trying to decide between Ferrite and Neo? Are the advantages really worth the price? All that and more answered in this video. What is up everybody, Deck here, and today I'm going to talk about the difference between neodymium magnets and ferrite magnets, in particular in the context of speakers. So first off, just going to start with a crash course in magnetics. Magnetic fields are described using magnetic field lines that flow from south to north. They form these big loops that go all the way around, such as this, and the further away you get, the more spread out they get, the weaker the field gets. Usually fields tend to be strongest in areas such as corners of magnets. Something else about magnets is they're always balanced, so there's no more north lines coming towards a magnet or south lines moving away from a magnet. They're always balanced. That is, if you were to put an imaginary circle around any magnet, the same number of field lines are coming out as going in, even if most of the magnet is south. What would happen in this case is you would get something like this. So all that really happens is the magnetic field is focused very tightly onto this spot right here. There's a lot of magnetic field here and not much here, as they're very spread out. Something else about magnets is magnetic fields try to spread out evenly across the surface when describing the average strength. So this would be what a weak magnet looks like. If that goes to infinity, you can just imagine either we're zoomed in really close so you can't see the curve, or this magnet just stretches and there's no place for the magnetic field to go around. So if you wanted to get a magnetic field strength twice as much, or if you wanted to have a twice as strong magnet, you would just have twice as many lines, just like this, twice as close. Magnetic field lines also like to go through usually ferrous materials. So instead of it just going out into the air like this, what will happen is it'll actually stay very tightly through this material here before spreading out. It always remains within this region here, but up the top you can see it arcs out a lot higher. Also, in a case like this, for example a horseshoe magnet, it would go straight from south to north, just like this, and you wouldn't have many extraneous fields around it. So this is why horseshoe magnets are very strong. A third example here looks more like a speaker, where you can see the field lines are all focused going through this material here, instead of spreading out like these ones up here. This is very good because what you can do is you can then take a chunk out and you'll still have these field lines going across, although they'll spread out a bit in the air, and you can put right here the voice coil of the speaker and have a really strong magnetic field right here. So now we can talk about neodymium magnets and ferrite magnets compared to each other. So the first, probably most noticeable difference about these two compression drivers right here, this one being neodymium, this one being ferrite, is this one right here is small and shiny. This one right here is large and more of a matte. It's a very dull material. So why exactly is that? Well, the first clue is with the chemistry. Now here's just a very quick bit about the chemistry of them. Neodymium magnets are typically this one right here, neodymium iron boron, which is about 72% by mass iron. So neodymium magnets actually have a lot of iron in them and not much neodymium itself. Ferrite magnets, on the other hand, are barium iron oxide. So ferrite right here, very typical, say for in speakers, barium with iron and oxygen. And this clue right here, it has a lot of oxygen in it, and this is why they're typically raw. The reason why is because neodymium magnets are often nickel coated because they're reactive. They've got a lot of iron, they rust very easily, so they're often coated with something like nickel. Whereas ferrite magnets are usually just left raw because they've got so much oxygen in them already, they don't really react or rust. But this actually leads on to the next clue about these two magnets. You can see this one here, 72% by mass is iron, and this one is only 68% by mass iron. So what about the density of the two magnets? The next example, here are two cubes of metals. This one 10 centimeters cubed, so this is 1 liter, and this one is also 1 liter. With the neodymium we end up with a density of around 7.5 kilograms per liter, and for iron we have around 5 kilograms per liter. So what's very interesting is iron actually has a density of 7.8 kilograms per litre, and both these have a lower density than iron. The reason why is because neodymium, even though it is a lot heavier an atom than iron, it's actually a lot less dense than iron. Neodymium is 7.1 kilograms per litre, whereas iron is 7.8, which is why it averages out to 7.5. And on the other hand, the ferromagnet, because it's got so much oxygen in it, which is a pretty damn light atom, it ends up having a much lower density. And yeah, what about the price of these two magnets? Now, of course, in, for example, a speaker, there's a lot more things that contribute to the price. For example, cone material, voice coil, spiders, all that sort of thing, the basket itself. But what about the magnets themselves? Neodymium typically costs $470 Australian per kilo, whereas ferrite magnets be as $32 per kilo. Now these numbers right here, I looked for quite a while to find a specific average price for them, but I just couldn't seem to find one anywhere. So you'll just have to take my word that on average, neodymium magnets cost say around $320 per kilogram, and an iron magnet weighs closer to $24 per kilogram. These are just arbitrary numbers that I found, but the main thing to take away from this is per kilogram neodymium magnets cost about 15 times more. So yeah, neodymium magnets are pretty damn expensive. And if we're looking at cost per litre, it goes up even more, $35.25 per litre as opposed to $160 per litre. So now we can see that it's over 20 times difference between the neodymium magnet and the ferrite magnet. But of course, we all know the most important spec about these magnets is how strong are they. Magnets are very difficult to grade in terms of strength, but for speakers, the most important spec of a magnet is how strong a magnetic field measured in Teslas it creates, or Gauss. 1 Tesla is 10,000 Gauss, by the way. A neodymium magnet can typically have a field strength of between 1 to 1.6 Teslas, whereas a ferrite magnet is 0.2 to 0.35 Teslas. So for the same size magnet, this, by the way, I'm going off 10 by 10 centimeters for an area of 100 square centimeters and a thickness of roughly 2.5 centimeters for both cases here. So neodymium magnets are a lot stronger than ferrite magnets. Going on a price to strength ratio, or strength to mass ratio, we can see that neodymium magnets end up having about, from the numbers I had above, they're about $880 for 1 Tesla across 100 square centimeters. This also requires about 1.875 kilograms of neodymium magnet. On the other hand, a ferromagnet requires about $200 because it needs 5 times the surface area. So to get 1 Tesla at 100 square centimeters, it needs 0.2 Teslas at 500 square centimeters, or 50 centimeters by 10 centimeters. And in order to do this, it also needs 6.25 kilograms. So just going off mass alone, you can see neodymium magnets are about 3.5 times stronger per weight and 5 times stronger per volume than iron magnets. And these specifications right here make them incredibly useful for compact speakers. And you really can see the difference up in these first diagrams. This ferrite magnet here looks like it could very easily take up about 5 times the volume of this tiny bit of neodymium magnet right here. And this neodymium magnet is actually stronger than this big iron magnet right here. So obviously cost is a drawback of neodymium magnets, but do they have any other drawbacks? Yeah, unfortunately they do. Just due to the strength of neodymium magnets and the way they're processed, often a ferrite magnet can be built into a speaker raw, as in you can put in a bit of ferrite which isn't even magnetic yet, you can assemble the whole speaker, you can then put it in a magnetizer, and bam, you now have a functioning speaker. Neodymium, on the other hand, is pretty well always magnetic through processing, which makes it very difficult to make speakers using, which is why it's so expensive. Something else magnets experience is as they get hotter, they get less and less magnetic, and eventually they reach a temperature where they just stop becoming magnetic forever. This is called the Curie point, and it varies depending on different types of magnets. For example, the lower grade a neodymium magnet it is, often the higher its Curie temperature, and vice versa. A stronger neodymium magnet can have a lower Curie temperature. Neodymium magnets can have a Curie temperature of as low as 80 degrees Celsius, which is below boiling point. I have seen videos of speakers that have been working and have got so hot you could boil water on the back of the magnets. If this was a neodymium magnet, it would have stopped working completely. The speaker wouldn't make any sound anymore. The coil inside it would just act as a pure resistor. The thing would very quickly overheat and melt. So neodymium magnets having a Curie temperature of 80 degrees Celsius, which is actually quite common in speakers, means these can sometimes not be so good for endurance and require a lot of cooling of the magnet itself to make sure it doesn't get too hot. Ferrite magnets, on the other hand, can be upwards of 350 degrees Celsius, which is well out of the temperature range of the voice coil. They're never going to get that hot. So as a standard ferrite, say subwoofer, gets hotter and hotter, its magnetic performance should stay quite flat. It can be very easy for a neodymium magnet to get up to 80 degrees Celsius as well in speakers, as for example, I live in Australia, and a temperature delta from say 50 degrees Celsius on a hot day in a hot car in the sun, even with the aircon on sometimes, means that it only requires a 30-degree temperature delta before the magnet could potentially stop working, which isn't that much power going into a speaker at all. Another thing too is neodymium magnets typically being smaller means they have a lower heat capacity, so they heat up more quickly. They do cool down more quickly, but they heat up more quickly than a ferrite magnet, which is just so big and heavy it soaks up a ton of heat. So definitely something I would take into account for example, a fourth order bandpass setup where magnets are going to be put inside the sealed chamber. 80 degrees Celsius also is about 180 degrees Fahrenheit, and 350 degrees Celsius is just a guess, probably around 600 degrees Fahrenheit. So yeah, hotter than an oven by a lot. So in summary, neodymium magnets are about 5 times stronger per volume than ferrite magnets, 3 times stronger per weight than ferrite magnets, but ferrite magnets are only 22.5% of the cost per relative strength of neodymium magnets, so about a fifth of the cost. And ferrite magnets are also easier to build a speaker with, as well as are less thermally sensitive once they're being used inside an enclosure. So neodymium magnets are about 5 times the strength of ferrite magnets. Well, now what? What does that actually do? There's a few really interesting things you can do with neodymium magnets that you can't really do with ferrite magnets. The first one is just a quick cross section of a standard magnet. It looks something like this. So yeah, this is just a really rough sketch of the cross section of a motor. You can see right here the flux would come up and around here, and in a neodymium motor, because it's so much stronger, what you can do is have a setup just like this, where you have a lot less neodymium magnet but get the same strength through roughly the same area. So this makes speakers that are made of neodymium a lot lighter. In fact, what you can do with some speakers is, if you imagine this is the cone here, if you put a wide voice coil on it, you can get the magnet to be so small that the entire magnet fits inside the voice coil of the speaker, instead of standard scenarios which need a giant magnet outside the speaker with the pole vent right there. Something else you can do with neodymium magnets, in fact some high-powered subs do this, is you can actually get the neodymium magnet and you can put it right up against the voice coil of the driver itself. And yeah, this is the technique Digital Design Z series subwoofers use. The magnet is right up against it, so its entire round about 1 Tesla magnetic field is in direct contact with the voice coil. Although these speakers, the big fins on them, as much as they'd probably help for cooling as well, they also help channel the flux around back to the rear of the magnet. Although these big fins are probably required, as I mentioned, voice coils can get a lot hotter than 80 degrees Celsius, so you really do want a lot of cooling applied to the neodymium magnet in order to prevent it from overheating and getting past the security point and just stopping, especially for a $5,000 subwoofer. That would be a real shame. Now, what's really interesting about this particular setup is the thickness of these rods that go around the exterior of the speaker are also about the same, say, thickness or area as the magnet itself. Now, the reason why is because the magnet would put out about 1 Tesla, and regular mild steel also has what's known as a saturation point of about 1 Tesla. Mild steel is the most common steel used in speakers because it's extremely cheap and very good at channeling magnetic flux, but some materials out there are even better at channeling magnetic flux, including a rare earth element called holmium. Now, I did a bit of research on it, and from what I can tell, pure holmium can transfer 4 Teslas worth of magnetic flux, and I believe there are some alloys that can transfer 5+ Teslas of magnetic flux. What this means is you can get a neodymium magnet and you can channel its flux down to a really skinny point. So say if you've got your voice coil right here, and what this would allow you to do, say these 2 voice coils are exactly the same and the amount of flux going through them is exactly the same. These voice coils will behave basically identically in a speaker, except this one right here has a lot more X max than this one right here. So basically, by channeling down the magnetic field, you get more excursion completely for free. This can also enable you to create a situation like this one right here, where you actually double the amount of magnetic field going through the voice coil and have the same excursion. Although cases where you see 4 Teslas or 5+ Teslas are incredibly rare, and the most common field strength you'll come across is from about 0.6 Teslas to a max of 2 Teslas, which is from a steel alloy. The main thing a magnetic field inside a speaker affects is a spec called the BL. The BL is very simply the magnetic field, which is the B, times the length of wire inside the magnetic field. It's measured in newtons per amp, which this means per right here, so newtons per amp. So for example, if you had a BL of 20, when you put 1 amp through a 1 meter long wire in a 1 Tesla magnetic field, you'll get 1 Newton worth of force out of the wire. And by the way, if the current is flowing in this direction, the force will be pushing across the magnet towards us. Now, of course, the higher the BL, the more strength a motor has. And the more strength it has is usually better because it makes it more efficient. What we can do is we have 2 options. The first option is to make this a 20 Tesla magnetic field, which is extremely ridiculous. Or alternatively, what we can do is we can actually take this bit of wire here and we can run it multiple times across and loop it back on itself, aka a coil, which is what pretty well all speakers do. They've got coils in them. So this is the most efficient way of having a system. Of course, you could also put more current through it, but then you're just stuck with the original super inefficient design. So inside a speaker, you have the voice coil right here, and you have a coil gap, and you have going through the coil gap the magnetic field. It's very common to have a magnetic field inside this gap of 1 to 2 Teslas, which means for a BL of 20 you need either 20 meters of wire for a 1 Tesla field or 10 meters of wire for a 2 Tesla field. And because 10 meters of wire has less resistance than 20 meters of wire, it's naturally a lot more efficient to have a stronger magnetic field. And of course, where do we get a stronger magnetic field? From neodymium magnets. So now I'm going to introduce two speaker equations. The first one is the efficiency of a speaker, which is NO, which is equal to 4 pi squared times the resonance of the speaker cubed times the VAS of a speaker divided by the speed of sound cubed times the QES, which is the electrical damping, which is basically the damping that the voice coil does. So how do we get the QES? QES is equal to the resistance of the voice coil divided by the BL squared, which is this thing up here, as I talked about, stronger magnetic field or more wire equals a higher BL, and this is multiplied by the square root the moving mass of the speaker, so how much the cone weighs, divided by the CMS, which is how stiff the cone is. So what does all this mean? Well, if, for example, what we get to do for the sake of simplicity is we get to just call this a constant, and also I'm going to call all this a constant, and we can see what happens is when we say, for example, go from a 1 Tesla field to a 10 Tesla field, if we were to take a standard speaker and replace its ferromagnet with a neodymium magnet with twice the strength, what would happen is the QES would go from, say, 1/1 relatively speaking squared to 1/2 relatively speaking squared, which is 1/4. So if our old QTS was 0.5, our new QTS would be 0.125, which is extremely low. This represents a lot of damping. But if you remember our equation up here, the efficiency is relative to basically a constant divided by QES. So if our new QES is 4 times smaller than our old QES, what actually happens is our efficiency is 4 times higher. So if our old efficiency was 1%, then our new efficiency is 4%, which might not sound very impressive, but it's basically 6 decibels for free. And yeah, 6 decibels is a lot. But something this figure here does not really express is just how much of an effect this extremely high damping has. So right here I have, now it looks like a bit of a mess, but these two speakers are exactly the same with a BL of 12.8, which is stock. These two speakers are exactly the same with a BL, everything else is kept the same. So you can see they've all got the same VAS and the same resonance, but this one has just simply a higher BL. So I basically put in that it's got a stronger magnetic field than it actually has. This third example down here has the strongest magnetic field of double the original figure of 12. And right here we can see basically a plot of how loud they are relative to each other. So what's really interesting is you'll see that the speaker which is loudest at the lowest frequency is actually the one with the lowest BL. And the reason why is because it also has the lowest damping. So this enables, for example, this yellow one right here, this yellow line right here. This one has the smoothest roll off as it works best in the biggest box. You can see with the orange one, it goes from 120 liters down to 35 liters, basically a quarter. You can see, although you can see here's the yellow line here and here's the orange line up here, so there is definitely an improvement in efficiency or sensitivity. You can see that due to it being a smaller ideal box to get the ideal damping, it ends up having a faster roll off than the yellow line right here, so it's got reduced output down low. And the red case, this extreme case right here, it has an extremely low QTS of 1.25, which means even though it's a 15-inch subwoofer, its ideal box volume is 4.8 liters, just over 5. So even though this one is the highest right up the top here, which is at about I believe 250 Hertz, you can see it very quickly rolls off and becomes the lowest output. So even though it has the highest BL, because it's got too much damping, it has a very fast roll off. And similar thing with the ideal ported boxes. You can see right here, this green line moves really smoothly down to 20 Hertz tuning from a 240 litre box. The blue line is 120 with a slightly higher tuning in order to still keep a nice curve. So it is just as loud for the most part, except this one starts to roll off at maybe 22 Hertz, whereas the other one works a bit better down to probably 80 Hertz. But you can see this one starts to roll off just below 30 Hertz. It's really hard to see, but this line right here is 30 Hertz. It'll probably be completely gone once this is rendered. But this one, the green line, rolls off after 20 Hertz. So you get about 10 Hertz extension from having a lower BL and a larger box. And this cyan one down here, it has a volume of 40 liters and a tuning of 28 Hertz in order to be most optimal. And it really starts rolling off at around the 30 Hertz mark. And it, watt for watt, is quieter than these two speakers. Even though these have a lower BL, it actually has reduced output until 100 Hertz, which is probably the highest frequency the subwoofer is going to be making anyway. So across the board, a lower BL ends up actually being better than a higher BL. So you may be thinking, hey, but that's not very fair, as what happens if you put the speaker with the most damping in the same volume box as the other ones? Will it then have more freedom to move at the low frequencies and have a greater output down low? Well, yeah, but only to a certain extent. You can see now what happens with the sealed side is the lowest damping has the highest output, still from about 100 Hertz down to 20 Hertz, which is the usable range anyway, all in the same volume boxes. The orange one from 100 Hertz down to about 20 Hertz, it then takes over, and it is smoother, so that is one thing, but you can also see it has a higher damping, which can also negatively affect sound quality. And you can see the red one down the bottom again, 120 liters. It is extremely flat roll off, and right down, it is actually the loudest out of all of them, but that's below 10 Hertz, which is basically inaudible for a single 15-inch driver in a sealed box anyway. And back onto ported boxes, you can see if all the tunings are the same and all the volumes are the same, this green line has the smoothest transition. This blue one now has a bit of a lump at tuning, and the cyan line, which is the highest BL, has a very distinct kick up. This is because the speaker's already so damped. When the tuning of the port starts to try to damp the speaker as well, it basically uses the BL to fight through it. So the cone moves still quite a lot, which means you end up hearing the port above everything else. So what, BL is always a bad thing? Is it always bad to have a high BL? No, it is actually not. A high BL sub with correct tuning, correct damping, this involves messing around with, as I showed before, this relationship right here between the moving mass and the compliance. If you fiddle with that, you can end up with a higher QES, which means less electrical damping, which means you can still keep a well-rounded subwoofer. The problem with this though is that means you need to increase the mass of the cone, which is usually happens just by having a more powerful voice coil in it. A heavier voice coil increases the moving mass and decreasing the compliance, which means making the cone stiffer. So a well-designed sub will take into account a high BL, and in particular subs with a really big cone area, such as 21-inch drivers or bigger, really do need a high BL in order to move the cone around with authority. If a very large sub was to use just a standard ferrite magnet, it would need to have an absolutely enormous motor on it in order to fight all the forces of the cone. I've seen some 33-inch subs which weigh, from memory, a quarter of a ton or something with ferrite magnets, so those would be very well off using neodymium magnets for the motor. All that theory is good and all, but it's a bit useless if you can't actually see an example of it in the real world. So here's just a quick example. Two compression drivers are pretty well exactly the same. These are SB Audience Rosso 44 CDN-PKs, by the way. So you can see with this speaker, it's Neodymium. It's got a flux of 1.85 Teslas. This other one is Ferrite with a flux of 1.59, so quite a bit less. The Ferrite one also has a sensitivity of 111 decibels at 1 watt 1 meter, whereas the Neodymium one has 112 decibels. All the other specs are pretty well identical. So you can see Neodymium, stronger magnet and a bit better sensitivity, even though, as you can see right here and mentioned before, the difference of the magnets. This Ferrite magnet is a lot larger than this Neodymium magnet. Something else you can see down here is the Neodymium version weighs 1.34 kilograms and the Ferrite version weighs 2.2 kilograms, so 900 grams more is just for the magnet. But of course the Neodymium one is more expensive. Here you can see on this website, Neodymium version for $260, the Ferrite version for $140. So it's almost twice as expensive to get the Neodymium version, and you get 1 extra decibel and roughly a kilo less weight. The Neodymium magnet version has a slightly smoother frequency response, something else to take into consideration. So what exactly are Neodymium speakers good for? Sealed sound quality units. As referenced before, they can have a nice frequency response roll off, and although they need to be put in a very small box in order to achieve their right QTS, they can have favorable characteristics. Compact. Just by having such a powerful magnet, you can really shrink the size of a speaker and also make the most out of small speakers where you need the most efficiency out of a small speaker, for example, Bluetooth speakers. Having a more powerful motor makes the most of the limited amount of energy the battery can hold. Lightweight and PA, which kind of goes hand in hand with compact. PA speakers, if they're lighter, they're easier to carry around. You can save money and trips on transportation of audio gear depending on the size of your business. Could possibly make as much difference as going from a 5 kilo Ferrite speaker to a 2 kilo Neodymium speaker. Fewer trips as you're not overloading, say, a van. Also, Ferrite speakers in PA speakers can really upset the balance of them and make them more awkward to carry, but if they're using Neodymium magnets, they can have a more central weight distribution. They're good for any situation where you've got a very large cone area to box volume ratio. They can get more out of smaller boxes. And lastly, SPL/compression. They're very good for high pressure, for example, a compression driver in a horn-loaded tweeter, as well as SPL competition where the more motor force you've got, the louder you get. Ported system, which is tuned to give the speaker a crap ton of damping, so you need as much motor force as possible to overcome that damping. So thanks for watching. Just a reminder, hit the like button and leave a comment if you've got anything to mention, say possibly your own experience or your own opinions on the matter. And if you're new and made it this far into the video, consider subscribing, as a lot of my videos are similar. And if you can sit all the way through this one, you definitely have the patience for all my other content. Yeah, thanks for watching and see ya.